Probably you have already heard this sound in several submarine movies, and today we want to investigate what this has to do with sea ice research. In this episode of Sea Ice Stories, we're looking into a topic that is called acoustic positioning. It is a method of determining the position of an underwater or under ice vehicle. But how do we measure position for a surface vehicle like a car or an airplane? Well, you nowadays all have GPS sensors even in your phone, and what GPS does, it is basically by an electromagnetic wave measuring the distance of your GPS receiver to 3 or 4 satellites that are orbiting the Earth in space, and by knowing the distances from those satellites you can actually recalculate your position on the surface of the Earth. When we go underwater, we have a significant problem because electromagnetic waves don't travel well in seawater. So it is very important to come up with an alternate method because GPS just doesn't work underwater or under sea ice. What can we do to solve this problem? Well, this is where acoustic positioning comes into play, and we're using a technology that is called Sonar. So Sonar stands for Sound, Navigation and Ranging, and the most easy application of Sonar that you probably know of is the depth sensor on a boat. So for example, this depth sensor is an acoustic source in the bottom of the boat that emits a sound pulse. This pulse travels to the seafloor, it gets reflected off the seafloor, and then the same sensor listens for the reflection of this sound signal. And when you know how long it took and you know the speed of sound of the water, you can determine how deep the water is in this point. For acoustic positioning, we basically do something very similar. There also our under ice or underwater vehicle sends out an acoustic pulse. This pulse is traveling through the water column. At some point it's reaching something which is called a transponder that is not reflecting the sound wave, but that is emitting a particular signal always when it hears a signal. So it is similar to a reflection, and when the vehicle then records this reflection, then we can calculate the time that it took for the signal to travel, and when we know the time, we know the distance to one of those transponders. So when we are able to place several transponders in multiple points, then we can determine the distances, or what we call the ranges, to several of those transponders, and then we can do the same thing as we do for GPS with the satellites, but just with our acoustic ranges, and triangulate the position that we are currently in. Now, of course, with Sonar you can also do other things. For example, on these transponders and acoustic networks, you can not only encode a simple ping for range measurements, but actually on the acoustic signal you can also encode data, just as you can encode data onto any electrical signal on a wire. So you can use acoustic communications, acoustic modems, to send remotely data to your underwater vehicle and command it home, for example. Last week I joined a field campaign on the fjord de Saguenay in Anse-Saint-Jean here in Quebec to test one of those systems that is meant for navigation but also communication with the Hugin AUV and for under ice deployments. So in Anse-Saint-Jean it was pretty cold, it was tough work, but we deployed 3 transponders in 3 positions throughout the fjord, and then we were able to check with a handheld transducer to communicate to those transponders and also to check if data is forwarded. Now you have an overview of acoustic positioning and Sonar works, and I want to show you a little example that we recorded last year on an expedition to the North Pole underneath the sea ice. In this example you can hear multiple acoustic devices that are pinging, and just listen to it for the first go and try to identify what you can hear as acoustic communication. It is quite obvious that in this recording we receive multiple signals from multiple devices, and to decipher that I show you a spectrogram of this recording. This is basically just a way of displaying when, in which frequency band there was how much sound energy. So we can play this again on the spectrogram, and then you see that we have one very strong signal, and that is the upsweep of the hydrosweep, the depth sensor of the icebreaker that is close to that recording. So you hear one very loud ping, and then a few seconds later on you hear a silent reflection of that exact ping, and then the ping starts again. Now we can determine the time that it takes from the pulse to be emitted at the boat and the reflection to be received, and this is 5.9 seconds. So now this sound wave has traveled from the ship to the bottom of the ocean and back to the surface where we hear it again. So if we want to determine the depth of the ocean at this spot, we have to divide this time by 2, which is 2.95 seconds. And if we assume a sound speed in water that is 1440 meters per second, we can easily calculate that the water depth in this particular spot was about 4250 meters. You see, we can already learn quite a lot of information just from looking at a simple acoustic spectrogram. There's other pings that we can see and locate in this spectrogram. For example, you hear these very regular, almost every second chirp noises that are made by the ROV, and they become more obvious once the ROV gets underneath the camera. And these are the pings that are associated with the acoustic positioning system. They are quite high in frequency, that's why they are high in the spectrogram, and they are our means of determining our position for the remotely operated vehicle under sea ice while we are in the field. I hope you learned a bit about how acoustic positioning and sonar is working and how we are using it underneath sea ice to navigate our robotic platforms. And with that, I want to thank you for watching and have a nice day.